Yes. Okay. So good evening again. So we continue from last time. We talked about the general ideas and components of robots. And we talked about localization and mapping and ROS, the Robot Operating System. And we'll continue with two more subjects in this overview. One is SLAM, Simultaneous Localization and Mapping. The other is a little bit about motion planning, and we will continue on motion planning, which will be kind of the beginning of this course, the main ideas of robot motion planning. So let's start with simultaneous localization mapping. And the first package for SLAM for ROS was started in 2007. It is called G-mapping. So the self-localization where the robot is done by odometry, by counting the rotation of the wheels and then calculating where the robot is, like integrating this over the time and finding where the robot is, and also a LiDAR to detect the obstacles and then map the environment. This worked okay, but not so good. Then in 2011, the Hector SLAM was introduced. So it is no longer depends for localization only on odometry. So it can use odometry, but not only, and can also be used without odometry. What it does a scan matching. This is the new thing here. It actually looks at the 3D, the 2D LiDAR map, and then detect some features on this map. And then when it moves, it sees how these features moved and calculate how the robot actually moved. This is called the scan matching. So it matched the scan, and from the matching of the scan, it calculates how much it moved. And also from the scan, it also knows the obstacles. So both of these things were new in 2011, and it was already possible to do SLAM online with a robot and only with a LiDAR, and this worked pretty well. But after a while, Google introduced the cartographer in 2016, and this is actually the most up-to-date package for ROS navigation. The ROS navigation or Nav2 stack is built on the cartographer idea. So it does two things. One is the scan matching, like the Hector SLAM. And the other thing is it has a global optimization and a local planning. So there is two layers. One is the local planning, which is probabilistic map. And then there is the global mapping, in which it finds where it was and does some kind of a loop closure. So when it gets back to a position that it already been there, then it knows where it is, and remove the error, reduce the error. And here there is a video with comparison of these three types of SLAM. The first, the top one, which is actually the last, is the cartographer and the HectorSlam and G mapping on the bottom. HectorSlam is without odometry. The other two use odometry as well, but not only odometry. And you'll see that after a few turns, both the G mapping and the HectorSlam kind of diverge, and the cartographer is giving actually good mapping at all time. You'll see it in a second. The ones on Zoom, do you see well the video?
Yes.
Okay, good. So you can see that already the HectorSlam and the G mapping kind of diverge and cannot figure out the orientation well enough, good enough, while the HectorSlam still maintain a good mapping of the room. And you see those black dots, which are the legs of the tables and chairs. At the level where the LiDAR sees them. Okay. I think that's it. Yes. Yeah.
Does the robot collide in things, or you know the distance between?
It knows the distance to obstacles because it has LiDAR, and therefore it actually computes its motion in order not to hit an obstacle. And this is exactly what cartographer is doing. It has the local planning that plan the motion locally and avoid the obstacles. So it has the global planner and the local planner.
The same thing that everyone should have on
Yes.
like maps, the robot.
The Xiaomi has LiDAR or cameras, just based on cameras.
I see in Xiaomi apps how
How the
robot
maps.
maps,
Yeah.
You see the really map of my kitchen.
Yes. Yes. So this is the main idea, the SLAM like here. And yeah, so let's continue. So the basics of robot motion planning, how to move from one point to another. So the problem of robot motion planning is how to find a continuous path in an environment that has obstacle, where the robot can move from start to target position without hitting the obstacles. You see, like the continuous path here, from start to target. Oh, you cannot see. Yeah, here. From start to target. A famous problem that was dealt with during the 1983 by Schwartz and Sharir from Tel Aviv University is the piano movers problem. So when you need to take a piano from one place at a house to another place, and you have obstacles like the walls, so you need to move the piano and also to change the orientation of the piano. So it's no longer two-dimensional space, it's actually a three-dimensional space because you can move it in X and Y and also rotate it in theta. So you have a navigation problem, which is a three degrees of freedom problem. And you have environment and you have obstacles, and you need to find a 3D a 3D path from the start to the target, because it is X, Y, and theta, so it's a 3D space. That's the idea, and that's the problem, the piano movers problem that Schwartz and Sharir found a solution to this. And when we talk about navigation, the objective is to program, to command the robot in a higher level programming language like Python or something else, to move from point A to point B, or from start to target. And the robot will automatically plan the motion in order to obey the command and follow the path from start to target. This is what we call navigation in robotics. In aeronautics, navigation is actually what we call localization, is to know where the airplane is. They call it navigation, we call it localization. So it's a little semantic. So we may have a few different tasks for robotics. One is localization, to know where the robot is, for the robot to find the position of itself, and also can be divided into two sub-problems. One is the when I know where the robot starts and I want to know where it went. This is one problem. The other problem is the kidnap robot problem. So someone kidnapped the robot and put it in some place, and now the robot needs to calculate where it is, to look at their surrounding, and based on what it sees, to know where it is. So this is two types of localization problem. The second is much more difficult. Even if you know the map, still, if you don't know where the robot is on the map, is much more difficult if you don't know the beginning point. Second problem or second task is navigation. How to plan a path without hitting an obstacle, to go from one place to another without hitting an obstacle. And even if you know the environment, you know the map, still it's a challenge to get to a certain place. Just imagine going into a place and then trying to understand what is the best way to take in order to get to a new place, to a new position. Then mapping. Mapping is to build a map, to sense an unknown environment and then build a map of this environment using the sensors. Exploration is like an extension of mapping. So if I need to go over the entire area and then build a map of the entire area, so I need to go into each place that the robot never been to, and see the obstacles there, and see the walls there, and then build the map of the entire area, not only the places that it went through. So it has to go to wander around the entire area. Coverage is similar problem, but here the robot has to go and move the sensor on every point of the environment, either a sensor or a tool. If we want to clean the floor, so the robot has to go over each point of the floor. This is the meaning of coverage. And of course, we do this and do some of the things simultaneously, like in SLAM. Some properties of the robot. About the robot's structure, the robot may have several degrees of freedom, can be either position and orientation. It can be a robotic arm with many joints. So it may have many degrees of freedom. And we have the task and the configuration space. I'll talk about the configuration space in few slides. But the task space is the space in which the robot actually does its task, like moving from one place to another, or moving a tool to clean the house. So this is the task, and the task space is the floor, or the floor, the XY, and then a rotation as well. And sometimes we have some constraints. The constraints, if we do not have constraints on the position orientation, it is called omnidirectional robot, as you can see here in the picture. So the robot can move to any direction. And we may have a robot with a non-holonomic constraint. A non-holonomic constraint is a constraint that the robot cannot have a velocity in certain directions. So we can imagine like the car. The car can move in the direction of the wheels, but cannot move sideways. So it cannot have a velocity in the sideways direction. It can move along some kind of an arc, but not sideways, not in the radius direction. And this is called a non-holonomic constraint. Also, for the robot, we may have a dynamic model of how the robot is moving. It can be either a kinematic model, where we input the velocities of the robot, like in the car, the speed forward and the speed of the steering wheel. And then we have a first order differential equation that governs the motion of the robot, of this car, per se. And we may have a dynamic model, which we have the entire dynamic second order differential equations, which are the equations of motions of the system, like in a drone that has 6 degrees of freedom equations of motion. And the control inputs are torques or forces, of the robot, and we also have the acceleration here, and it's a second order differential equation. So this is kind of the properties of the robot. Now, when we want to plan the motion, we will have some algorithm, and this algorithm that is a set of commands to the robot, what to do in which case. And this algorithm has some properties, may have some properties. One of them is optimal, where the algorithm is optimal, which is optimal algorithm solves the problem optimally with respect to either path, length, travel time, energy consumption, or whatever cost function that we want, but it actually minimizes this kind of cost function along the way and find the optimal path. It has some complexity. We'll talk about this in a minute. It is called computational complexity. It measures how good the algorithm performs in terms of the size of the problem. So if I need to navigate in a large map, so how many computation we have in terms of the size of this map. And we can, or how much memory we need. Also, this is the next bullet, is memory consumption. But complexity can be calculated in worst case, what is the environment in which the algorithm perform the worst. If I can kind of build such environment that the algorithm would have to do a lot of computation there. And we can also calculate this in the average case. We can run it on many types of environments and calculate the average time or length that it takes to solve this problem. Also, we have the memory consumption, which is also part of the algorithm, property of the algorithm. Memory consumption, we can have either constant memory, so a certain amount of memory is allocated for this algorithm, and all the time just use what the memory that has. It can be polynomial memory, so it is some kind of a polynomial in the size of the problem or in the size of the map. The amount of memory that the algorithm needs, and can be also exponential memory. So it is exponential in the size of the problem. In this case, we can solve only small problems, problems that are not big, because exponential of this would be very large. And usually we don't have so much memory. Another key property of an algorithm is its completeness. We say that algorithm is complete. The planning algorithm is called complete if it returns a feasible solution if such exists. So it finds a path if there is a path, and if there is not a path, then it returns a message, a fail message, in a finite time. So it does not look for a path over and over again and never stops. So it stops in a finite time and says there is no solution if there is no solution. So it's either finding the solution or either stopping and saying there is no solution. This is the completeness. Another two properties is whether the algorithm or the motion planning algorithm solve the problem offline or online. Offline, it means that the environment, the map of the environment and the obstacles is given a priori before starting the motion. So I know what is around me, and I know where I want to go, and I can plan the motion before I start walking. So the whole path is calculated in advance. And then there is the online motion planning. In online motion planning, we do not know the environment, the map of the environment and the obstacles. We don't know them in advance. We use the robot sensors in order to build the map while the robot is moving. So the robot is planning the motion during the sensing the environment, and then continuously building the path. This is called a sensor-based navigation. So you can see at the bottom, a robot is moving. It doesn't know that there is an obstacle. This is an online motion problem. It doesn't know that there is an obstacle, but when it finds the obstacle using its sensors, then it replans the path in order to avoid the obstacle and go around it and reach the target. Now, let's talk about workspace. We define workspace, and sometimes this is called also task space. As I told you, this is the space in which the robot performs its task. It can be a two-dimensional space, it can be a three-dimensional, the world space. Sometimes we have obstacles in the space of the robot. Then we call them workspace obstacles, WOI. W is the workspace, as you can see here. And the free space is W free, is the entire space without the union of all the obstacles. So we have each obstacle, and the union of all the obstacles is the places where the robot cannot be. So you can see here, this is the workspace of this robotic arm, and this is some kind of a workspace obstacle. There is something there that the robot cannot hit. Now, in contrast to workspace, which is the 3D space or 2D space that we know, there is also the configuration space. So configuration space, it is marked with the letter Q. So I'll give it as an example. For a 2D robotic arm, which has two angles, so the configuration space is the parameters of the configuration of the robot. So here it's θ1 and θ2. These are the two parameters of the configuration space. And you can see here, θ1, θ2, this entire box here on the right. Yeah, here, this entire box here, this is the configuration space in which the robot can move. can go from 0 to 2 pi because it's rotational. And because it's rotational, its topology is like a torus. You see here, because the first angle can move in 360, and also the second angle can move 360. So we have like the outer part, the boundary of a torus. This is the topology of the configuration space, but we don't use this so much. We use kind of this space, and we say it can be warped around it. So 0 and 2 pi are the same. What?
Where is that signal? That's that point. Where the point that the arm doesn't know where to go, to the minus theta or plus theta?
It's the same. Minus theta and minus pi and it's singular.
Singular,
Singular point. So it can move through singular points.
Where is the singular point from this? Right.
I think it's here, this point. Yeah, here or 0. 0 and 2 pi of both. And pi also. Yeah. 0, 2 pi and pi, and also in the center. But it doesn't matter because the robot can move through a singular point. It's not a problem. It's a computational problem, but not real. It's a real point that the robot can move through. So this is the configuration space, and we usually plan the motion in the configuration space, because this is the space in which we command the robot. We command it in θ1 and θ2. And also in the configuration space, there are some configuration obstacles. So if we have a robot arm and there is an obstacle in the workspace, so this obstacle is mapped to the whole angles, θ1, θ2, in which the robot collide with the obstacle. So QOI is the configuration obstacle. And if we say R of Q is all the points, are all the points in the workspace that belongs to robot R when it is in configuration Q. Q is a vector of all the angles of the arm. So this R of Q is actually where the robot is, where each point of the robot is. So the configuration obstacles are such configurations Q is vector. When R intersect in the intersection of R with the obstacle, with the workspace obstacle, so when the robot and the obstacle actually have common points, it means that the robot actually collide or overlaps the obstacle. When it's not empty, there are points which are both on the robot and on the obstacle. Such configurations are forbidden, and these are a configuration which belongs to the configuration obstacles. And you can see them here in the gray area. Here in the gray area. And you can see them as the obstacle, the configuration obstacle. This is the entire configuration obstacle, and also it is warped around both in θ1 and θ2. And the free configuration space is the entire space the entire configuration space when the union of all the configuration obstacle is subtracted from this entire space, entire configuration space. So again, when we want to plan a motion for this robotic arm around this obstacle, we have to move in this free space, free configuration space here. And we can move through 0 to the 360 or and back here to the other side, from the other side of the obstacle. So let's say we have a rectangular robot, the orange one. I'm losing the, yeah. This is the robot. You see the orange one is the robot, and it has a local frame, reference frame. This is the local reference frame of the robot. And there is the blue obstacle. And the robot can move in X and Y and can also rotate in theta. So the configuration space is X, Y, and theta. And if we map all the points where the robot hits the obstacle, we get this configuration obstacle. So now it's a 3D space because it's X, Y, and theta. And for each theta, we have a set, like a plane, like a polygon of configurations, XY configurations, in which the robot cannot be because it intersects with the obstacle. So if we want to plan the motion of the robot, we need to plan here from one position orientation to another position and orientation in the configuration space. And we need to find a path without hitting the obstacle. So you can see here that a motion path is a continuous path in the free configuration space. So we have a parameter C such that is the goal point, the target point, and C of parameter S, which S is from 0 to 1, belongs to the free configurations space. And this is for all S between 0 and 1. And you see here, you can see here the path that starts from the start, go around and get to the target. And this path is actually can be mapped to the X, Y, and rotation of the orange robot to go around the blue obstacle. And although the entire task space is two-dimensional, you see that the configuration space in this case is three-dimensional. And sometimes if we want to navigate a box in a 3D space, then it is the task space will be three-dimensional, but the configuration space will be six-dimensional, X, Y, Z, and three rotations. So this sets the problem. Now we want to start and see this. This is the entire notation of what we are looking for in a motion planning algorithm, and what's the environment in which we are working. And then we want to start and see if we can design some motion planning algorithms for robots. We'll start from very simple problems and then analyze the algorithm and then advance further. Finally, we will learn how Waze is working, more or less. So, do you want to take a break now, or no? We'll take now, I think, before we start the algorithms. Then after the break, we'll talk about bug algorithms. Zoom recording. Yes. Okay. So let's discuss the set of bug algorithms for motion planning. As the name suggests, they are kind of inspired from insects. And insects have only local knowledge of the environment. So it's an online motion planning algorithm. It is for simple robots with no constraints, and they require some local knowledge to accomplish some task. So the assumptions are as follow: the robot is a point. We do not consider the size of the robot, or we can say it is a disk. And then we actually inflate some of the obstacles in the radius of the disk, so the center point of the disk can go only around the obstacle. So the robot is a point. The robot has an ideal localization sensor, so it knows where it is at every time, all the time. And the robot has a touch sensor to identify the obstacles, the obstacle boundaries. So when it touches an obstacle, it knows that there is an obstacle there. And the entire workspace is finite and closed. So it cannot go to infinity. Those are the assumptions. So, yeah, let's start with the planning. So the bugs know the direction to the goal. So it knows where it is. It knows where the goal. So it knows the direction from the start to the goal. Bugs know the Euclidean distance between any point, any 2 points. So it can measure distance from current point, say, to the target. And other sensing is local, so it is only when touching the obstacle. So what do you think the bug should do? Any idea how to get from start to target?
We burn the return and start to collide the obstacle. And after you do the pass the obstacle, you're going to see. Yeah.
Go around.
Go around and fix the time or the distance to go near the obstacle and then go to the goal again.
Yeah, you're on the right direction. So bug zero is very simple. First, go towards the goal. Then, when it hits an obstacle, go around the obstacle in an arbitrary direction, either right or left. Here it's left. And then measure the distance to the, not measure the distance. When it sees the goal, just leave the obstacle and go directly to the goal.
What would have happened if it to the right?
Then there is no solution. Or it would go and hit the other obstacle. Yeah,
Why decide to go left and not right?
it's just arbitrarily.
But,
It doesn't important. So we said, oh, whatever. Yeah. We said at the beginning that when it hits an obstacle, it goes left. Okay, we could have said it goes right. But it doesn't work. As you have said, we can design an obstacle that it won't work. And you can see such an obstacle here.
because it has to turn right to get into the.
Here, let's say when it goes, same thing, when it goes left, here, it will go directly, then go left, then hit the obstacle, and again, go left, cannot leave the obstacle,
Yeah.
go, get here again, and we continue that way, and the goal is trapped in a circle, and the algorithm won't work. So it's not a good idea. So in this case, in this kind of an obstacle, the algorithm will not find a path to the target. So what else we can do? So the problem here, it doesn't know how to go back and measure the distance and see that there is something problematic. It doesn't have memory. So if we add some memory, we can do something better. What we can do?
You get it a lot. Like, the obstacle, you know what they do. Then you can use go the other direction.
So here's bug one. Bug one will work. It goes like this. First, go directly towards the target. Then when it hits an obstacle, just go around the entire obstacle and measure the distance to the target in each point of the obstacle. When it finds a point on the boundary of the obstacle that is closest to the target, then go back there, leave the obstacle there and go directly to the target. And if it hits another obstacle, do it again. This is the idea. So let's see. So what it does here, it first goes towards the target. Then when it hits an obstacle, it goes around the obstacle. And while moving towards the obstacle, when moving towards the obstacle, it measures the distance from each point to the target. And it finds that this point is the closest to the target. So this will be the first lead point. Then the robot did the whole circle and went back to the lead point. From there, go directly to the target. From there, hit another obstacle, again, does the entire circle around the obstacle, and then find that this point is the closest to the target.
Yeah, but when you know, when you do all the obstacles, in the next loop,
It can choose the direction which is the closest.
no, but you don't need to go, you know where the obstacle, so you don't need to go in, start with the obstacle, you can do the obstacle.
Like here,
After you do the first loop, we find the point, we find the other obstacle. The next time, when you run again, you don't need to start with the obstacles again. And go in the optimized way.
Huh.
Okay, you see,
I did the loop, then what?
I did that loop, not to the obstacle. You go
What?
the loop, you go to the goal point. Okay? And the
How?
next time,
I went from here, went towards the target. I didn't know that there is an obstacle.
okay.
So it hits the obstacle, then go around, then what?
Okay.
Okay? So this idea, understood? It looks a little inefficient because I have to go, the robot has to go about 1.5 times around each obstacle. Almost 1.5 times. So it looks inefficient, but it will find the solution if such exists. And it won't be trapped, which is more important. So let's discuss the upper and lower bound of the length of the path that we have here. So this is kind of a complexity analysis, but it's not actually computational complexity, but it is the length kind of complexity. So if there are no obstacles, the shortest path is like the direct line from start to target. But if there are obstacles, so at most we'll go 1.5 times around each obstacle. So the upper bound of the length of the path is d plus 1.5 times the sum of the boundaries of the obstacles.
Amir, does it mean that after he's mapping the obstacle, he will take the shortest route to the optimal points?
Yes.
Okay.
Yes, it will take the, let's go back. Here. One path to the goal is blocked, so there is an obstacle. X is the point where the obstacle was met. This is the point. Then follow the obstacle edge all the way around. N, the minimum distance to the goal. So N will be the point from which the distance to the goal is the minimum.
But he will take the shortest route between X and N? That's the question.
Yes, so it will be either from left or from right. It will choose
The shortest.
the shortest one because now we already remember. Then go to N. You see, go to N is the shortest to N. Yes. Okay. And you can see another thing is that on every lead point, the distance to the target is reduced. Because otherwise, this will be the lead point. If there's not, if this was not total, this will be the lead point, but it cannot be. So, and then it will say there's no solution. So, how we can say that or show that it is complete? Algorithm is complete if in finite time it finds a path if such a path exists, or terminates with a failure if it does not exist. So it is either say there's no solution or it finds the solution. So how we can actually prove this? We suppose that bug is not complete. Therefore, there is a path from start to goal, even if there is not, no, we're incomplete. Therefore, there is a path from start to goal. By assumption, it is finite length and intersect obstacles a finite number of times. And that bug one does not exist, does not find the solution if it exists. Either it terminates incorrectly, so it stopped, or it spends an infinite amount of time looking for the path. Suppose it never terminates, but each leave point is closer to the obstacle than the hit point when it hits the obstacle. So it lives in a shorter distance to the obstacle. So it all the time it gets closer and closer to the target. So eventually it will get to the target. And it will not be infinite because there are finite obstacles and finite number of hitting and leave point. Each hit point closer than the last leave point. Thus, there are a finite number of hit-leave pairs. After exhausting them, the robot will proceed to the goal and terminate. Because it's finite number, so it will reach the target and not look for a solution for infinite time. And suppose it terminates incorrectly, then the closest point after a hit must be a leave point, where it would have to move into the obstacle. But it cannot move into the obstacle, therefore it has to stop and say that there is no solution. But then line from robot to goal must intersect obstacle even number of times. But then there is another intersection point on the boundary closer to the object. Since we assume there is a path, we must have crossed this point on boundary, which contradicts the definition of a leave point. So this is the idea, and this is the proof that it is complete, and it will find the solution if such exists, and will stop if it's not exist. Now we can improve this. This this was kind of inefficient because we had to go around the obstacles. But maybe we can find something that is a little better. So bug 2 is doing something a little different. So it says there is a line from start to target, and this line intersects the obstacles. So now what we are doing, we're moving along the line until we hit an obstacle. When we hit an obstacle, we go around until we intersect with the line again. When we get to the line again, we continue to follow the line to get to the target. So we follow the line again, and then you see, we follow the line again, we hit another obstacle, we go around the obstacle until we get to the line again, and then continue straight to the target. This looks much more efficient, right? And we can do this either from right or from left. And here you can see this is called the M line. This is the line. While pass through the door is blocked, follow an obstacle edge. If M line met, then break and go back. Go along, follow the M line, and then go back. And you see that every hit point and lead point, we are advancing along the line. This will be a key in the proof of completeness. So, what happened here? Well, not at the goal. Well, this is the same thing. Here. From start here to target here. So from start, it goes from here, go back, and then this is the start now. So it goes from here until it hits an obstacle, then go around the obstacle and get back to the line, and then continue. And then there is a circle here. So there is a problem.
And with a condition to go to start twice.
There should be something like this. Let's see how to fix it. And I'm next closer to the goal. So if we go around either from left or from right. We go and we cannot here. It's not closer to the goal. So we are not advancing. So we want to leave there. We go all the way until the lead point here. So this is the correction. Okay. You can see here the how we compare if we take the right direction, right turn, or left turn, or no. No. This is bug 1, this is bug 2. Yes. Okay. Sorry. This is the orange is bug 1, the red is bug 2, and you see that bug 2 is much more efficient. But
So question, whether we can choose the unline during the such as if we move in the top left corner and we recalculate the underline and top as well.
So, but this is bug one. Bug one is changing actually the end line.
I mean, party bug two is.
Oh, if you take from here and do,
Yeah, and we recalculate the underline and.
maybe it's possible. So for this environment, we see that bug two beats bug one. But what about this environment? Let's see. Oh. Let's see. If we take bug one and go from here to here, then bug one will take this point and then move all around and this all around until it gets here and move back, right? This is bug one. What would bug two do? It will go directly and then do this entire thing and then, right? No, here, no, it cannot move here, but here it will move back and then do again this entire thing until it gets to this point here and then move back and do again all the time around, and it will be less efficient here. So bug one is exhaustive. It considers all the choices before progressing. Bug two is greedy. It goes towards the target. It's greedy algorithm. Takes the first thing that looks better. Bug two will often outperform bug one, will be better than bug one, but is less predictable. Because in some environments, it can be worse. So, if we want to go, if we want to compute the boundaries, so the lower boundary is again the shortest path from start to target. The upper bound is actually half times the boundary of the obstacle, but we have n times intersections with the obstacle. So every time it intersects with an obstacle, it goes half the way of the obstacle, approximately, in a mean way. So this n may be large because in the in bug one there was not this n. You remember there was, let's go back, there was 1.5 times pi. So this is the boundary, but here we have ni over 2 times pi. So if n is larger than 3, this is worse than the first. And we don't know this n in advance. That's the problem, because n depends on the environment. So those who developed debug algorithms were Lumelsky and Stepanov. In 87. Okay. So this is the end of this presentation. I'll go to the presentation of the next class. I go faster than usual, but that's okay because we have less weeks this semester. And you don't have many questions. So that's okay. So how does Waze works? If we want to go from one place to another, Waze actually calculate the best route, right? And also avoid traffic. How does it do this?
The inputs from other drivers.
That's okay, but how to compute it? Now I'll give you the whole map, and also how much time it takes to go from one intersection to another. How to compute? What is the best route? What? That's one option. Yes. But anyone here knows what is the answer? No. How do you know? Yeah, okay. You are not from mechanical engineering. What? You are now yes, but your background? Oh, so you know all about graphs. So this is not what we are doing now. Okay. So we build a graph that database. So for you it's familiar, but for mechanical engineers it's new, I think, for most of them. And so a graph database is a database that has vertices and edges. So you see here, like the intersection and the roads that we saw on the map. So this is the intersection, and those are the roads. So we have vertices, V1, 2, 3, 4, and 5, and we have the roads, which are the edges of the graph, in which we can move from one vertex to another. That's the idea. So a graph, is a set of vertices and edges. This is the database. And just a notion, V2 and V3 are adjacent because they have an edge connecting them. And edge 2 is incident with a vertex 2. So this is just the notion. So if we want to navigate, and this is for the first part of your work, and if we want to navigate a robot in 2D, but it has also the orientation. So we have, and there are obstacles. So the entire configuration space is this, and we can discretize the configuration space, and we can also discretize the obstacle in which those are the points where the robot cannot be. So we have this entire configuration space, and now it is discretized. And if we want to move to plan a motion in this configuration space, we want to move from one point to another. and we say that each point here on this discretized configuration space, we said it's a node or a vertex of the graph, and each line here that connects two vertices is an edge, and if there is a vertex inside the obstacle, we just remove it. And we remove also the edges that go into the obstacle. And then we can find the shortest path along these edges and vertices, exactly the same as we do on roads and intersections, as I showed you before. But this will be in a 3D space. It's the same thing, but here the list of vertices are the points, and list of edges are the lines that connect to points which are adjacent. You understand? What? So now, to hold this database, we can set an adjacency matrix. We say actually which are the vertices and what is the what edges connect to vertices. So from vertex 1 to vertex 2 we have E1. From 1 to 2 we have E1. And from say vertex 5 to 3, 5 to 3 we have edge. What happened?
We have 3 and 5. There is like
3 and 5.
we have 2 edges.
Yeah,
It's the number of
it's the number of edges. Yeah, here. But I think it actually should be, or maybe the distance here. But it has to be the list of the, here's just the number of edges, but it has to be the number, the index of the edge. And the graph can be also a directed graph. The directed graph is like a one-way street that you can go only in one way, the direction of the arrow. So not every edge ij is not like ji, because there is direction. Yes. Oh, and here it's a weighted graph. So we said there is traffic, it takes a lot of time. So if it takes a lot of time, I can say, or it's longer distance between these two intersections, I can say this weight of this edge is larger. And then I would like to find a way that has a total weight which is the smallest. And I can weight them in different types of weight. It can be length, it can be time to go. So if there is traffic, it will be more time, not the distance, but the time. In ways you can say that you want also
without the roads.
What?
Without roads, that was the more.
Yeah, things like this, or a road that has better view. I think there's such an option there. So let's do some definition. A path in a graph is a set of vertices Vj, set of vertices, such that an edge Ej, j plus 1 connect any adjacent vertices Vj and Vj plus 1. So it's a set of vertices that are edges that connect them. This is a path. that I can go from one vertex to another through the edge. A path is connected, and this is another definition, if there is a path between any two vertices. So I'll say what is not a connected graph if I had vertices here and vertices here, and there's no edges that connects them. So like an island. So if there is an island, it's not connected. If I can go from any point to another, it is connected. A cycle in a graph is a path that starts and ends in the same vertex. So it's a path that goes all the way through many vertices and ends at the same point. This is a cycle. And a tree is a graph which is connected. So there is a path from any point to another, but it does not connect, it does not has a cycle. A tree is a connected acyclic graph. So it's a graph which is connected with no cycles. So it has a root and then it just go all the way, and it's not it does not contain any cycles. In complexity, we talk the big O notation. In order to classify, notation is used to classify algorithms according to how their runtime or space requirements grow as the input size grow. So it's just an order of magnitude. It's not the actual time or actual computation, amounts of computation needed. It's just the order of magnitude. An order of growth is a set of functions whose asymptotically growth behavior is considered equivalent. So it's the same order of magnitude. For example, 2n. If n is the input, the size of the input, so 2n, 100n, and n plus 1 is the same order of magnitude because it's linear in n. So it doesn't matter that here the coefficient is 2 and here's 100 and here's only 1, because it's the same, it grows the same as the input grows. It's linear with n, and we say it is order of n, O of n. This is the big O notation. And this is called linear. And it can be polynomial. Polynomial, so if it's here, it's n squared or n to the 3. So this is a polynomial. And so this is order of 1 is constant. So this is a constant number of computations for, it doesn't depend on the size of the input. Order of log n, and this is a little over this, because all log n is more than constant but less than linear. And order of n is linear. Order of n log n is a little more than this. This is quadratic or polynomial, quadratic, cubic, and some coefficient to the power of n. This is exponential because this grows exponentially as n grows. And if we have algorithm which is exponential, then What happened? Can you see the screen?
No,
Why? What? Did you see up until now?
yes, up until the complexity slide.
This, only this slide.
Yes, and
Okay.
the explanations until the exponential.
Okay, so you didn't miss much. And you had the explanation, right?
Yes.
Okay. All right. So now, how do we compare a searching algorithm? Will it find the solution? Will it find the best solution? So first, we defined what is a complete search algorithm. A search algorithm is complete if whenever at least one solution exists, the algorithm is guaranteed to find a solution within a finite amount of time. So it will find a solution if such exists. And it is optimal if the search algorithm will find the best solution. So this is things that we want to see about our algorithm, whether they are complete and optimal. We want also to measure the time complexity. The time complexity of search algorithm is an expression for the worst case amount of time it will take to run. So if we want to find a path, this is the most amount of time that it will take. In worst case, for the worst graph there is, it will what will be the time expressed in terms of the maximum path length and the maximum branching factor. This is for trees. We'll talk about branching factor in a minute. And space complexity, again, is the expression for the worst case amount of memory that the algorithm will use, the number of nodes it has to remember, and also expressed in terms of M, the path length, and B, the branching factor, which we'll talk about it in a minute. So we will talk about a few search algorithms for searching a path from start to target on a graph database. So we want to find the set of vertices in which are connected through edges from the start to the end. This is the path. So DFS is a depth first search. It's a greedy algorithm that goes directly to the target. It has a graph. It can be directed or undirected graph. It has the adjacency list representation of the nodes of the vertices and the edges. And the goal is to systematically explore every vertex and every edge from the start to the target. I think maybe before I start this, let's have a break and then continue this after the break. Didn't look at the time. Okay. So let's continue. So we talk about depth first search. So it's a search that systematically explores every vertex and every edge in order to find a path from the start to the goal along the graph, along the vertices of the graph. And the idea is to search deeper when it's possible, to go towards the goal as fast as possible. We use a stack here, מחסנית, where we insert new objects or new vertices from this side. And when we need to pick a vertex, we take also from this side. So it's like a magazine, like a stack, when we put from the top and we also remove one from the top or from the left side here. And let's see how it works. Also, we use here some colors just as a database. So we color the vertices to indicate their state. When we change state, we change their color. Each vertex is, at the beginning, it is white. When it is discovered, we first look at it, it is gray. And when we finish processing it, it is black. So it will be either white when we didn't see it anymore yet. It will be gray when we saw it. And when we finish processing it, it will be black. Records discovery of a white vertex during scanning, adjacent U by U goes to the stack. So U is the parent of V. If we have two vertices that we go from U to V, or we saw V from U, then U will be said to be the parent of the V. So we went from U to V, so U is the parent. So every time or for every vertex, we remember how we get to it. We have a pointer to the back vertex. And the procedure is very simple. It gets the graph and the initial vertex. Let S be a stack, so we initiate a stack as well. We push into the stack the vertex V, which is the beginning vertex, while S is not empty. When the stack is not empty, we do this. First, we pop a vertex from the stack, and we call it V. If V is not labeled as discovered, it's not gray, then label V as discovered. So put a color gray to V. And for all edges from V to W in the adjacent edges V, so all the nodes, the vertices which are around V, and we can go to them, we put them into the stack. We put them one by one into the stack. And all those that we saw. If V is the target, then stop, because we found the way to the target. and we can go back along the pointers, the back pointers of V to its parent and to the back, the previous one, and then to its parent, and then so on. Let's have an example. So this is our graph. You see vertex 1, 2, 3, 4, 5, 6, 7. You see the edges. And we start from vertex 1, and the target is vertex 6. So this is the first that we start, and this is the one that we end, and we need to find a path. So the discovered list is empty. The stack at the beginning is empty. Then we started V1. So what do? We put it in the stack. So we put V1 into the stack with no back pointer because it's the first one. So there is null pointer here. Then from 1, we look at its neighbors. From 1, its neighbors are 2, 3, and 4. You see? Because we can get from 1 to 2, 3, and 4. So we add those to the stack. 2, 3, and 4 with back pointer to 1, because we get to 2 from 1. And we move the vertex 1 to the discovered list. So this was the second step. Now I look at the stack, and pop the first one in order to be in the discovered. So this is what we'll do. The first one from the right. So I took the last one from the stack and put it in discovered. So now I move to here, the first one from the right, and look at its neighbors. Its neighbors are 5 and 1, but 1 is already discovered. So I don't touch it anymore. I already saw it. So I put only 5. 5 with a back pointer to 4, because we went there from 4. And then next step, we'll pop the last one from the stack. So it will be 5. Yeah. So we move here. We move 5 from the stack. And we look at its neighbors. Its neighbors are only 2. But 2 is already in the stack. So I don't touch it. Because I already saw it. So we just add this to the discover. We didn't discover the target anymore yet. So we continue. The next one in the stack will be 3. So we will move to 3. And from 3, we will discover, we will put 6 into the stack. So we add 3 with the back pointer to 1, because this is how it was in the stack. And then from 3, we see 6. So we add 6 with back pointer to 3. And now the next stage, we will pop the right one from the stack. So we'll take it, and then when it will be discovered, it will be the end. You see, we found the last one is the target, and that's it. So now we go from 6 to 3, and from 3 to 1 along the back pointers. So the path is from 6 to 3, from 3 to 1, and from 1 to 9. So this is the back track of the pointer, and we can read it from right and see the path from the start to target. So this is the idea of depth first. It goes directly to the target, as much directly as it can towards the target. Here's an example. The textual example, you see how it searches the path along this maze until it finds a solution to the target. So the path cost is 105. And that's it. So the runtime, the times it takes, or the amount of vertices or computation that it needs to look for is at maximum the number of vertices plus the number of edges, because it has to go over all of them in the wall space. The memory is O of H, the length of the longest simple, without repetition, without circle, path in the graph. So the longest path in the graph is at most the memory, because in most way I need to fill the stack with all these vertices along this way, this path. To explore the graph and find a solution, a path, and we search wider in the nearest vertices first. So it searches in the circles that are growing like waves, and that it search, and also sometimes it is called like bush fire because it expands like a fire. We use here, instead of a stack like before, we use a FIFO quo. A quo is a first in, first out quo. So we insert parts here and we pick from the last. First in, first out, not like before, the stack was last in, first out. Now it's first in, first out.
Amir, we can't see the screen.
I don't know why, but I'll share it again.
Thank you.
It's only this slide, right?
Yes.
Okay. So this is the idea for this. We have a queue and not a stack, which is a first in, first out. And the search is from the start, we search the closest vertices, and then we grow it like a fire or like a wave, and then explore the entire graph until we reach the target. And then when we reach the target, we know that our path will be the shortest because we enlarge the circle one step at a time, the search circle. So you can see here the order in which we explore the tree, the graph, not the tree. So the procedure is like this. We get the graph, we get the root, which is the beginning or the start node, the start vertex. We initiate a queue and then label a root as explore. This is like the gray, I think. Q in Q root, we insert into the Q the first vertex. While Q is not empty, we do first, we take a node, a vertex from the Q, we take it out. If it's the goal, then we return this vertex. If it's not the goal, for all edges from V to W in the adjacent edges of V, so all the vertices which are near V, they have edges to V. Those are W, those are all the edges. If W is not labeled as explored, then label W as explored and insert it into the queue. That's the idea. And let's do an example. So we start with this graph, and the start node, the start vertex is one, this one, and the last one is 9, this one, and the explored vertex is empty, and the queue is, we start with initiating the queue with the first vertex. So we need to go from 1 to 9 along the edges and find the shortest path. So what do? We first look at 1 and look at its all neighbors, which is 2, 3, and 4, and put them into the queue and put 1 into explore. This is what we do in the first step. In the first step, we put 1 into explore and then put 2, 3, and 4 with their parents, with their parent 1, the back pointer 1, into the queue. Now we know in the queue, we take the oldest one. Not the first, not the last one as before, but the first one, which is 2. So we take 2, we put it into explore, and then add its neighbors, which is 5 and 9, into the queue. So we add from here and take from here. This is a queue. So we add 5 and 9, and we take the next one will be 3. And you see that we explore first the ones which are closer to 1. This is the first level, and then we will have the second level, which is this. So we add added 3 and its neighbor 7 here with back pointer to 3. Well, next we'll take from the left. We'll take 4 into explore. And we take 4 and put it into explore and look at its neighbors. It's only 8 because at 1 we already did. So it's only 8. And we add 8 with a back pointer to 4. And then we take the left one, which is 5. As you can see here, 5 from here. This will be the next one. We add 5. And then 5 has no neighbors because at 2 we already did. We already explored them. So we do not go back. We just go forward. And there is no neighbors to 5. So we add nothing to the 4. And we continue. The next one will be 9 with a back pointer to 2. So we go to 9 with a back pointer to 2. And now 9 is the target. So we finish. So we can go from 9 to 2, and from 2 to 1, and from 1 to 9. And this is the path, the back path. From 9 to 2, from 2 to 1, from 1 to 9, and we can go to the other direction from 1 to 2 to 9. From 1 to 9. This is the shortest path to 9. This is BFS. And we have a simulation here of BFS. You can see that it explores the closest first. So it is less fast, slower than DFS, but it systematically finds a way, and when it finds a solution, this is the shortest solution. So, about the complexity. So for DFS and for BFS, the runtime is the same because at the worst case, we need to go over all the vertices and all the edges. The memory here, it's only the length of the longest simple path. And here, worst case, we'll need to add the entire graph into the core, and therefore it's longest. It's more memory. But in worst case, H is also can be V plus E. I told you that we will discuss a tree. A tree is a special case of a graph. A tree is a graph with no circles. So you can see a tree has a root and has branches. And B is the number of branches in every vertex. So here the branching factor is 2 because we have 2 branches. And D is the depth of the tree. You see, it has 1, 2, and 3 levels. This is the depth of the tree. Here it's 3. And we can calculate the B plus C, the number of vertices and edges, like B is the number of branches to B, because if we have 2 at every level, so it's 2 over 2 over 2, and so on. So it's an exponent. Okay. Now let's talk about a list and the complexity of searching an item in a list. So if I have a list and I need to find this number 20. 20 is in some kind of a cell, in a cell in the list. So the simple thing to do, just go one by one, ask every cell if it's 20. If yes, then stop. If not, continue to the next one. So this is a linear search. The complexity here is the order of the length of the list. How many items? In the worst case, we will want to find an item which will be the last one. Then we will have to go over all the items. This is the worst case. Therefore, the complexity is order of n, the length of the list. But if the list is a sorted array, so if the list is sorted, and so here we have like 9 cells, but the numbers in the cells are sorted from the smallest to the largest. And I need to find a specific number. What do? I go, so this is a binary search. So we go to I go to the center. And I ask, is it bigger or smaller than the one that I'm looking for? So here we are looking for set for 23. I go here. Is it bigger or larger than 23? It's smaller. Is it bigger or smaller? It's smaller than 23. Therefore, I can throw half of the list. And now I have only half of the list that I know that 23 is there. Then I go to the middle of the next half of the list, here. I go here, 56 is larger than 23 that I'm looking for. So I can throw the rest of the list here, the right side. And now I'm left with 38 and 16. 16 I already saw, so it's only 23. So this is like every time I throw half of the element, and when I need to get and put an item into the list, still again I need to find the location where to put it. I need also to find in the exact place, so I need to do the search in order to put an item into the list, and also to find an item in the list. So in each step, I throw half of the elements. So first I have n, then I have n over 2, then n over 2 to k in the k step. This is the number of elements that are left. In order to find the last one, I need to that n over 2 to the k step, will be 1. So this means that 2 to the power of k is equal 1, and k, the number of steps, will be log to the base of 2 of n, log n. So the complexity, the number of steps that I need to do in order to find the right position will be order of log n in order to search for an item in a sorted list. And it will be the same in order to put an item into a sorted list. Therefore, it is much more efficient to have a list which is sorted and then look for an item in this way, then look for an item as before, order of n, which is larger than log. We have 10 minutes. And A star is really important. So I want to do this next week. So we'll stop here 10 minutes before. And we'll see next week that we'll use this search method in order to use and implement more efficiently the A star algorithm to find the shortest path, which is, I think so, the way that Waze is searching. So we'll see this next week, same time, same place. You're welcome.
תודה, אמיר.
And Bedma?